Some more vocabulary. All right, state. What is a state? Right. Usually, when I ask this question in class, I get some sarcastic responses, be like, "Oh, Pennsylvania," or "Oh, my state right now is confusion." Right. Trying to trying to be funny aside, a state is a very important term with thermodynamics as well. A state is basically a point of equilibrium where all properties of the system are at fixed values, and that completely describes the condition of a system, right? So the first thing that comes to mind sometimes with state is that, oh, it's people think of phase, right? I'm in a gaseous state, or a solid state, or a liquid state, and that is part of it. But I can have uh, um, an infinite number of gaseous states. So, say for example, I have, or I can have I have air, right? That's at 90 degrees Fahrenheit. Well, that's one state, but also if I have air at 80 degrees Fahrenheit, that's another state. Both of them are gases, but they have different states because the temperatures and the other properties are different. That's just an example. If I want to describe the state, right, there's several thermodynamic properties we're going to deal with. I'm going to write them out, but you don't need to know them all at this point. Excuse me. You don't need to know them all at this point, but the properties are temperature, pressure, specific volume, internal energy, enthalpy, and entropy. These four properties are specific. They're per mass. They're listed as per mass in the back of the book. These are not. What I'm getting at is with these six thermodynamic properties, if I define any two of them, say for example temperature and pressure, I can quantify the other four, right? And so we need two properties to determine any state. Equilibrium. Equilibrium is a state of balance where there's no unbalanced driving potentials, right? So if you're at a specific state, you should be at pretty much an equilibrium state, is what we call it. There's different types of equilibrium. There's mechanical, phase, chemical, and thermal. We're not necessarily going to be covering all of these in class, but those are the different types of equilibrium that we look at. What we're really interested in is thermodynamic equilibrium. Thermodynamic equilibrium is equilibrium with respect to all possible changes of state. And that brings us to something called the state postulate. Right? The state of a simple compressible system is completely described by two independent intensive properties. What does that mean? That means basically what I said in the prior slide. If I list all of my properties, again, which I don't expect you to know at this point, but we will study at a later point. If I list all my properties, I need to know two of these independent properties in order to quantify the other four. Okay? That is what this state postulate is saying. And a simple compressible system is just a system in the absence of electrical, magnetic, gravitational motion, and surface tensions, right? So it's just basically a state of equilibrium of which I can quantify all the properties by knowing any two. And that describes what I say describes the state of the system. Just to make sure we're clear, the word independent property means one property can be varied while the other is held constant, right? So for example, if I have, I don't know, let's say water vapor, right? Water vapor, which is basically steam. If I have water vapor that's at a temperature of, I don't know, 150 Fahrenheit and a pressure of, let's say, 500 kilopascals, I can still keep my my water vapor at 150 Fahrenheit, and I can change my pressure to 600 kilopascals. So basically, my pressure changed independent of what the temperature was. I did not need to change the temperature in order to change the pressure, for example. I can change one independent of the other. That's what independent property means. Moving on, state, then we have process. Right, what's a process? A process is any change from one equilibrium state to another. Right, so a process is basically, if I'm changing from one state to another, how did that occur? Right, so let's say my water, I have water in a pot, right? And I'm cooking it above a fire, right? My water over time is increasing in temperature. So let's say at one point the temperature is 90 Fahrenheit, and then I record the temperature again later, it's at 100 Fahrenheit. I went from state 1, where my pressure was at 90 Fahrenheit and 1 atmosphere of pressure, and then state 2, my pressure was still at 1 atmosphere, but my temperature went up to 150 degrees Fahrenheit, right? That change of state occurred because of a heating process. So that heating process caused a change in state. And then, in addition to a process, each process has what's called a path, right? And a path is a series of states a system passes through during a process. So for example, let's say I have a graph here, right? On the y-axis, I have one property, and on the x-axis, I have another property. I go from state 1 to state 2. The way that that process happens is called a path. Why is it important to know the path? So I'm going to take a second to explain that a little bit because it's very important to understand what a path is. A path is not only important to understand the process, like how did you change state, but it's important how it happened. Right, let's look at the image of a desk. Right, I have this is my bad image of a desk on a floor. And I want to move, actually, you know what? Let me redraw this. Let's say I'm looking at a room from the top, right? So this is a room. I have an object right here, and I'm moving the object to this point right here. So we'll call that state 1 and state 2. So I'm moving the object, I'm pushing it across the floor to this point. Let's say this is 5 meters of distance, right? So it took a certain amount of work for me to push this object from point 1 to point 2. And that amount of work is basically the work that it took to overcome the friction effect on the floor to move it 5 meters. Right? So that state 1 is position 1, state 2 is position 2. But let's say instead I took this desk and I dragged it across the room and moved it to here. So, and let's say this distance is more, right? The cumulative distance is more. The change in state's the same. I went from this point to this point. That's the final result of what I did. But the way that I did it was different between this path and that path. This path obviously took less work than this path, right? So what I'm getting at is the amount of work that it took to move that desk depends how it happened. It depends on how I moved it. Did I just drag it directly from point 1 to point 2, or did I take a detour across the room, dragging it across the floor, resulting in the need for more work? Work is something called a path-dependent function. So it's not just important to know how the system changed state from point 1 to point 2, it's also important on how the process occurred. Right? An example of that is that we're going to learn in the next chapter that work is pressure times change in volume. Or sorry, the integral, if I really want to get specific, when I'm looking at work, I can define work as the integral of P dV. Again, I'm not so concerned that you understand everything behind that right now, but let's just use this as an example, the integral of P dV. So if I were to plot that, I would have pressure on the y-axis and volume on the x-axis. So let's say I have one pressure and one volume at state 1, and I have another pressure and another volume at state 2. And let's say that this is the way that the work was being put in the system to cause this pressure and volume change, right? So if you look at the integral, the area underneath the curve, right, if I integrate that, basically it equates to that the amount of work, this number W, would be the result of the area under the curve. But what if I did a different type of work? What if the path was this way? Right? Obviously there's more area under the curve, which means that this work value would increase. It's the same correlation as I said here. If I decided to move this from directly across the room from point 1 to point 2, that requires less work than moving it all the way across the room, or all the way around the room to point 2, from point 1 to point 2. So the state change, the actual linear distance between point 1 and point 2, the position change is the same, but the amount of work that it took to make it happen was different. So basically what this is basically getting to is that to completely describe a process, one must know the initial and final states, right? Initial and final state, as well as the path the process follows. So it's important to know both of those concepts in order to completely describe a process. One such process we're going to look at is something called a quasistatic or a quasi-equilibrium process. That basically is a process that proceeds in a manner that the system remains infinitesimally close to an equilibrium state. What does that mean? Let's say let's just say, for example, I have a tank, right? Now, if I were to go ahead or a piston cylinder, so if I'm going to go ahead and compress this really quickly, really fast compression, right? Really fast compression, what happens? The temperature goes up. But if I decide to compress it slowly enough so that the temperature never actually increases, what I have is called a quasi-equilibrium process, meaning that if I stop at any point, I'm going to be at equilibrium. If I compress this really quick, what happens is that the temperature goes up, the pressure goes up, and then as it sits there, after I compress it, the temperature will eventually go back down, causing the pressure to go down. Right? But if I go ahead and I do a slow compression, well, the pressure is going to gradually go up, and the temperature is just going to remain constant. Right? So that's what's called a quasi-equilibrium process. All right, I hope you guys are following. There's a lot of things to absorb here. Cycle. This is the next thing. What is a cycle? Well, a cycle is a series of processes that start and end at the same point. So here's back to a diagram. So let's look at this graph. We have pressure on the y-axis. We have volume on the x-axis. Here's state 1. Here's state 2. A cycle basically will start at state 1 and also end at state 1. So I need at least 2 processes, right? The process to go from state 1 to state 2, and then the process to return to state 1 from state 2. Now, a cycle can have any number of processes, but the point is that it always comes back to the same state that it started. All right, so that's a cycle. We're going to be dealing a lot and later on in the class on what different types of thermodynamic cycles. Next thing I want to look at are what we would call iso properties. What does iso mean? Iso basically means staying the same, right? So an iso process is a process where a certain property remains constant, right? What do I mean by that? Well, for example, if I have a process that is isothermal, what does isothermal mean? Well, isothermal means a process that happens at which the temperature remains constant. What does isobaric mean? Isobaric means a process that occurs where the pressure remains constant. Isochoric is another example of a process that occurs where the volume remains constant. Right? Remember I told you that if I want to describe a state, I need at least 2 properties, right? So I have 2 properties to describe one state, and let's say I'm going through a process that goes from state 1 to state 2. I need 2 properties between these 2 states. What's great about an iso process is that, for example, if I know the temperature at state 1 and it's an isothermal process to state 2, the temperature at state 2 would equal the temperature at state 1. So automatically, due to me knowing the type of process it is, I can already know one of the 2 properties that I need at state 2 in relation to state 1. All right. Some processes that we're going to be dealing a lot with are what we would call steady processes, steady flow processes, right? Steady flow basically means a process that has no change in time. A steady flow process is one in which a fluid flows through a controlled volume steadily. So here's an example. Let's say I have a tank here, right? I have a tank, I have water flowing in and water flowing out. Inside this control volume, inside this tank, The fluid properties can change with location within this tank, within this control volume, but at any fixed point they remain the same during the entire process. So let's say I have a time here, I have a time stamp of 1 p.m. This process is occurring steadily. At this location, the temperature is at 300 degrees Celsius. Well, at 3 p.m., the temperature of that location is still at 300 degrees Celsius. But any change for maybe the water at this location is 250, this location is 225, so forth and so on, right? The dimensional change, the position change, the temperature is different, but over time, it's the same. Steady flow processes are important, and we're going to be using them pretty often in this class.